In modern life and industry, magnetic materials play a crucial role. For magnetic materials, we mainly utilize their magnetism and the magnetic field they generate to work. Different devices or items have different requirements for magnetic materials. Therefore, it is particularly important to choose the most suitable magnetic material, based on performance requirements and working environment. In this video, we will introduce how to measure the performance level of magnetic materials, including 4 main performance indicators: remanence, coercivity, intrinsic coercivity, and maximum energy product. Remanence is the magnetization left behind in a magnetic material after an external magnetic field is removed. Colloquially, when a magnet is magnetized, it has remanence. Its symbol is Br, and its units are Tesla, T, and Gaussian, G. 1 Tesla equals 10,000 Gauss. The limit value of remanence is called saturation remanence. First, a huge magnetic field is applied that saturates the magnet's remanence, and then the external magnetic field is removed. At this time, the remanence is saturation remanence. The remanence of a magnet is mainly determined by its microstructure, and factors such as raw materials and processing technology can affect it. For example, in neodymium magnets, the addition of lanthanum and cerium can reduce the remanence of the magnet, but due to their very cheap prices, they can reduce the cost of raw materials. Increasing the proportion of neodymium can significantly increase the remanence of magnets, but the cost will increase significantly. In addition, reducing contact with oxygen during the manufacturing process can also improve the remanence of neodymium magnets. Coercivity is a measure of the ability of magnetic material to withstand an external magnetic field without becoming demagnetized. Coercivity is measured in units of Ørsted or kiloampere per meter, and expressed as Hc or Hcb. Under the action of an external magnetic field, the magnetic flux density of the magnet weakens with the increase of the external magnetic field. The Hcb point is the applied magnetic field intensity corresponding to a magnetic flux density of 0. But at this point, the magnetization of the magnet itself is not 0. If the external magnetic field is removed, the magnet still has a certain degree of magnetism. When the reverse magnetic field intensity reaches the Hcb point, although the magnetic induction intensity of the magnet exhibits 0, the magnetic polarization intensity is not 0 at this time. When the reverse magnetic field reaches the Hcj point, the remanence decreases to 0, and the magnet completely loses its magnetism. As the reverse magnetic field intensity continues to increase, the magnetic polarization intensity of the magnet decreases very slowly. But when the reverse magnetic field exceeds a certain level, the magnetic polarization intensity will rapidly decrease. Usually, we refer to the point on the intrinsic demagnetization curve with J equals 0.9 Br as the knee point, which corresponds to the magnetic field of Hk. When the external magnetic field is greater than Hk, it will cause huge and irreversible magnetic losses. The squareness of the intrinsic demagnetization curve is also an important attribute of the magnets. The closer Q is to 1, the closer the intrinsic demagnetization curve is to a square, resulting in better performance. The maximum energy product is an important standard that reflects the strength of permanent magnet materials. It is the maximally product of magnetic flux density and magnetic field intensity. Maximum energy product can be graphically defined as the area of the largest rectangle that can be drawn in the second quadrant of the BH loop. Although humans invented the first magnetic product as early as the 3rd century BC, it was not until the development of the KS steel magnet in 1917 that a magnet with an energy product of close to 1 megagauss Ørsteds was produced. Afterwards, the improvement in the performance of permanent magnets became very rapid. The 20th century was a great period of innovation in permanent magnets, including the development of aluminum nickel cobalt, ferrite, samarium cobalt, and neodymium magnets, which were the 4 most important discoveries in the history of the industry. Between 1930 and the early 1980s, energy product increased by a factor of 50 and intrinsic coercivity by a factor of 100. As of this date, sintered neodymium magnets remain the reigning permanent magnet champion with commercial products as high as 52 megagauss Oersteds. If you find the video helpful, please like and follow us. Your support is the best encouragement for us. If you are interested in our products, you can also browse our website or contact us. See you next time.